Hello, and welcome to 5-Minute Math. Today we are looking at the 7th grade concept of constant rates of change. This is 7.4a Readiness Practice, the advanced version. If you are interested in exploring the 7.4a Readiness Practice for the intermediate or proficient version, or the Readiness Practice resource aligned with any other standard, you can find those by using the link in the video description. All right, so we've got two different friends running a race here. And we have our distance is going to be y, and then our time is going to be x. All right, and so let's go ahead and label our axes here to figure out what kind of scale we want once we figure out what is actually happening. So Ashley starts 30 meters ahead of the starting line and runs at a constant rate of 5 meters per second. So let's do this. Let's have our distances just go, I'm seeing a 30 and a 5. Let's label this by 5s. Now you might have chosen a different, so we'll end up looking at the same answer, but our graphs might be different if you didn't skip count by 5s. Maybe you skip counted by 10s. If you tried to skip count by 1s, hopefully you figured out that you ran out of room really quick. So let's get this going right here, and we can use two different colors to represent Ashley and Brandon. Now we might skip count by 5s for our time, or we might use a different scale factor. Because what we're doing is we're doing per second here. And so I'm thinking for our time, it might be easier for us just to use a scale factor of 1, because it's just, we're going to be doing 1 second at a time. And if we try to do 2 seconds at a time or 3 seconds at a time, it's going to make our graphs a little bit difficult to manage. So you can use different scale factors if it requires it. So let's get up here to 20. All right, so now let's start with Ashley. So Ashley starts 30 meters ahead of the starting line, which is not fair, but maybe Ashley needs a head start. So at 0 seconds, I'm going to make Ashley this purple right here. At 0 seconds, Ashley is already 30 meters ahead. Okay? Runs at a constant rate of 5 meters per second. So at 1 second, she's 5 meters. At 2 seconds, she's another 5 meters. So you see how we're just going up? We're basically just joining, or we're jumping up where each of these lines join. And we're just going like this. So she's got a constant rate, 30-second head start, and we're just moving at 5 seconds each. So let's see if we can get a line that's going to best represent that. And we'll just have it look like this. Okay. Now, let's look at our friend Brandon. Now, Brandon's going to start at the starting line. So he's going to start here. Let's get that. There we go. So he's starting at the origin. But he runs at a constant rate. Look at that. 7 meters per second. Okay, so Ashley does have a head start, but Brandon is actually going faster. When will Brandon catch up? Well, at 1 second, our distance is going to be 7. So we're going to have to estimate a little bit here, but we're skip counting by 7. So let's zoom in here so we can get a little bit more precise, right? So we're going to be at 7. So I'm going to put that right there. Next, we're going to be at 14. Next, we're going to be at 21, right? I'm just skip counting by 7s. Then I've got 28. You notice how that's a steeper slope? I can get right there, 5 and 35, right? So that's going to help. So now I've got 42. 49 is almost 50. I've got the 56, just past the 55. I've got the 63. And then I'm at 70. So we're getting closer. You notice how the distance is narrowing. Let's keep going. So 77. Then I've got 83. Let's see. So 70, 77, that's actually 84, excuse me. 91. And then I need 98. and then we're almost off. So this next one is going to be 105. So let's make one more right here. Let's make another line. Let's pretend that's like right there. And I'm going to extend this right up here. Let's make that blue. And we'll just kind of go, we'll pretend like it goes right up there. And there we go. Let's make this go right up here. So this is going to need to be 105. So let's bring this down a little bit. It's actually going to be right here. So at this point, we are at 105. When we are at, how many seconds is this? This is 15 seconds. So my x is 15. My y, my distance is 105. Well, let's extend up what we have right here. We're going to be at that exact same spot, right? Because we're just going up by fives each time. So 15, 105. So that is where he catches up, right there. So when will Brandon catch up with Ashley? So we will say, after 15 seconds, Brandon finally catches up with Ashley. That is our answer right there. So we know that they catch up because that is when their two lines finally touch each other. So let me draw a straight line here, starting at the origin. I'm going to go all the way up through that point. And then I'm going to extend this purple line that we already have. I just got to make it a little bit farther. And you notice where they touch, that intersection, that is our solution. That is where we can find they catch up to each other. All right, so we've got two trains now that are traveling at constant speeds, and we're going to make a table. Okay, so let's make a table. So I'm going to make this train A, and train A leaves the station at 10 a.m., so let's do a time. And then travels at a constant speed, so after 30 minutes, okay, so I'm going to do 10. And let's say they leave the station, so the distance is going to be 0. Constant speed. After 30 minutes, train A was 30 miles away. Okay, so let's just put that as 10:30. I've got 30 miles, so it's constant speed. That's pretty easy. I've got train B, and so let's do this. I'm going to kind of extend this right here. I'm just going to make time distance, kind of jump over. This one is going to be train B. So train B, what do we know about that? Train B leaves the same station at 11 a.m. Okay, so if I want to keep things the same, what I'm going to do is I'm going to put those times. 10 o'clock, still at the station. 10:30, still at the station. At 11 o'clock, still at the station, right? Leaves at 11, and after 30 minutes, now train B is 40 miles away. All right, so train B is 40 miles away, so I'm going to say at 11:30, we are going to be at 40 miles away. So that's my constant rate there is I've got that 30 miles in 30 minutes for train A. I've got 40 miles in 30 minutes for train B. And then we need to figure out what happens at 11, 12, 1. So my rate right here is per half hour. Let's figure out what I have per hour. So I'm going to go ahead and extend this down. I'm going to have 11. So that's going to be 60. So really I'm doing 60 miles an hour here. I'll go ahead and add my 11:30 so I can keep it the same, right? So that's going to be 90. And let's get each of these up to noon. Let's get each of these to noon. And then after that, instead of doing the 30 minutes, I'm going to do an hour each. Because here's my unit rate is going to be, so this is 60 miles per hour. This is 80 miles per hour. I need to use these tables to figure out when train B will overtake train A. So you see that train A has a 40-mile head start. So let's now go to, I did 11 o'clock, 12 o'clock. Let's do 1 o'clock. Okay, so I'm not going to add 30 and 40. I'm going to add that 1680 because that 30 and 40 was per 30 minutes. So this is going to be 180, and this is going to be 160. So you see how train B is catching up. Train B is only 20 miles behind now. Let's do 2 o'clock. I'm going to add another 60, 240. And then I say 2 o'clock. That's going to be 80. Look at that, 240. So they are at the exact same distance. Hopefully they're on parallel tracks. And then at 3 o'clock, we can see now that that's at 300, but now train B is passed because train B started later but is at a faster rate. So now we are at 320. So train B will overtake train A right there at 2 o'clock. So let's just put that 2 o'clock p.m. is when they are even, right? If we were graphing them, that's where these two lines would touch. And then beyond that, every second beyond that, train B is now faster or farther than train A. For our third problem, we have a company producing widgets at a fixed rate, right? So we can use our direct variation, y equals kx. When they produced 8 widgets, it cost $500. Okay, so C is going to represent the total cost of production. W is going to represent the number of widgets produced. So we can actually kind of replace this, right? The C is the total cost. So we can say our C equals, I'm just going to replace my Y with my C, and then my W is going to represent my X. Now, I need to find my constant. What is my unit rate? I know how much it costs to produce 8 widgets. I want to figure out my unit rate, how much it costs to produce 1 widget. And remember, your K also equals, if we divide both sides by X, Y over X. So in this case, we're using C and W, so K equals C over W. And they told you that the total cost was 500 for 8. So let's just divide that 8 into 500. And that's going to be 648. And that's 20. It's going to be 2, 16. Add a decimal. And that's 5. $62.50 is how much it costs to produce 1 widget. So that's my K. So 62.5. So $62.50. So if I want to write an equation, I am going to go back to this original. Now that I know my K, my unit cost, I'm going to go back to that, and I'm going to bring that over here. I am going to use the C and the W. So I'm going to say my cost equals, I don't need the dollar sign, 62.5, because that's my unit cost per widget. For every widget, it costs $62.50, and that will be my answer. So if you are interested in exploring the 7.4a readiness practice for the intermediate or proficient versions, or this 7th grade readiness practice along with any other standard, you can find those by using the link in the video description.